Here's another released FRQ from the AP exams, this one from the BC exam of 2016. This is number 4. So again, anything that's going to have a number 3, 4, 5, or 6 is going to be a non-calculator question. Consider the differential equation dy dx equals x squared minus 1/2 y. Notice this is non-separable because of the minus here. There's nothing we can do to separate this using methods that we've learned in the class. So we're not going to have to find this using the solution using antiderivatives, but we can still do lots of other things. For example, we can find d squared y dx squared. Well, we know that d squared y dx squared is the derivative with respect to x of dy dx. And we know that dy dx is x squared minus 1/2 y. And we know that we can take derivatives of x squared to get 2x, and derivative of negative 1/2 y will be negative 1/2 times dy dx, right? Because the derivative of y is dy dx. And we can do the substitution here. We can replace dy dx with x squared minus 1/2 y. You can feel free to leave the answer like this, or if you feel like it, you can distribute the negative 1/2. My recommendation is to leave it like this unless you're compelled to do some sort of simplification later on. Okay, great. So part B, let y equal f of x be the particular solution to the given differential equation whose graph passes through the point negative 2, 8. Does the graph of f have a relative minimum, relative maximum, or neither at the point negative 2, 8? Well, in order for a differentiable function to have a maximum or a minimum, we must first check the slope, the derivative of the function, or I guess I'll call it a function, at that point. We're going to evaluate dy dx at negative 2, 8. So we're going to take x squared minus 1/2 of y, where x equals negative 2 and y equals 8. And we get 4 minus 4, which is equal to 0, which does not tell us much yet, except that the tangent line is horizontal. But we can now use our answer from the previous problem, d squared y dx squared, evaluate that at negative 2, 8, and we'll get 2 times negative 2 minus 1/2 of, I feel like we just evaluated this, right? We just did that here, and we got 0. So we end up with, well, I'll write it up here, we end up with negative 4, which is less than 0, is the relevance there. So the justification here of saying that our second derivative is less than 0 is pretty important. We have to indicate that the reason we care about the second derivative is because it's giving us a negative value. Because f of x, f prime of, let's just say, because f prime of negative 2 is equal to 0, and f double prime of negative 2 is negative, negative 2, 8 is a relative, well, which one is it? It's concave down, so that means that we're making a frown, and at the horizontal tangent line, that must be a maximum. This is a relative maximum based on the second derivative test. All right, great. So part C, see a limit. The first thing you want to try is maybe direct substitution. This is a new particular solution, g of x, with a new initial value of negative 1, 2. We're going to evaluate the limit. Well, let's take a look at what g of negative 1 minus 2 over 3 times x plus 1 squared is. Well, that's going to give us, well, g of negative 1, we're told, is 2. And down here, negative 1 in here is going to give us 3 times 0 squared. Uh-oh, we get 0 over 0. So that's going to be a situation where we want to use L'Hopital's rule. So in L'Hopital's rule, we want to make sure we explicitly state that the limit as x approaches negative 1 of the numerator is equal to 0, and the limit as x approaches -1 of the denominator is also equal to 0, we have to state that the limit of the top equals 0 and the limit of the bottom equals 0. So L'Hopital's rule, L'Hopital says that the limit is equal to the limit of the derivative of the top divided by the derivative of the bottom. So the limit as x approaches -1 of g of x minus 2 over 3 times x plus 1 squared is equal to the limit as x approaches -1 of, let's see, the derivative of g of x is g prime of x. Derivative of -2 is 0. Derivative of the denominator is 6 times x plus 1. Okay? Well, what is g prime of x? Well, g prime of x is equal to dy dx, right? G prime of x is equal to, where do we have it? We have it up here. X squared minus 1/2 y. At the point -2, 1. So at the point -2, 1, or sorry, -1, 2, we'll plug in 1 for x, -1 for x, and we'll plug in 2 for y, and oh my goodness, we get 0 again. And on the bottom, we also get 0 again. So we'll use L'Hopital's rule one more time. And you know what? Maybe we have to state the limits again. I don't really feel like it. I'm getting lazy. Sorry, guys, but I'm just going to do L'Hopital's rule one more time, and we'll see that we're looking for the second derivative at -2, 1. I keep on doing that. -1, 2. So g double prime of x is equal to, again, our second derivative, which we found right here at the beginning, 2x minus 1/2, and I'll just go ahead and write it as dy dx because I know what dy dx is already. It's equal to 0. We just found that. So g double prime of -1 is equal to 2 times -1, which is -2. So we can actually evaluate this limit to be -2 over 6, which is -1/3, and that is our final answer. So L'Hopital's rule twice is required for that one. And then finally we have part D, which is Euler's method, which is what we just learned in that last video. We'll start with an x value of 0 and a y value of 2. This is a new particular solution. We'll find our slope. We'll use that to find our change in y, and we'll use that to find our new y value. Okay, we're trying to get to an x value of 1. We're using 2 steps, so what goes in the middle? I think we all know that 1/2 goes in the middle, right? Delta x is equal to b minus a over n, which is 1/2. All right, so we have to evaluate dy dx at 0, 2. And if we do that, we get, there's x squared. So 0 squared, I forget what it is, x squared minus 1/2 y, minus 1/2 y. So that's -1. Multiply the dy dx times the delta x to get our delta y value of -1/2. We had an old y value of 2. We're going to add delta y to get 3/2. Okay, we have to evaluate dy dx at this new point, 1/2, 3/2. So that's going to be x squared minus 1/2 y, or 1/4 minus 3/4, which is -1/2. So our new slope is -1/2. Multiply that by our delta x of 1/2, we get -1/4. So our old y value of 3/2 is getting changed by -1/4. So the new final y value is 6 minus 1 is 5, 5/4. So I would probably go ahead and write as a final answer, outside of all my work, h of 1 is approximately equal to 5/4.